Hello, welcome to one of two videos about integrals and methods of integration. In the end, you'll learn about why we use certain methods over others and how each method works. The first method of integration I want to speak about is the power rule. It's a basic method of integration. Now let's start with the derivative. The derivative of x cubed. So something raised to the power of something, in this case to the power of 3. By the power rule of derivatives, we know what to do here. Drop the power, subtract 1 from the power, and we end up with 3x squared. And we also know that integration is basically the reverse operation of differentiation. So when we integrate the derivative, we arrive at the original function. So if we integrate 3x squared dx, we would get x cubed, which is the original function, plus c, some constant that would just disappear when we differentiate the function. And we already know in our case, c is just 0, because our original function is just x cubed. Now here's how we solve it if we didn't know the original function x cubed. So our task is to integrate 3x squared. We need the power rule. And to understand the power rule, it's good to use what we have, the information we have. We won't usually be provided with this, because our task is to just find the integral, or our task is usually just to integrate this function here. But what we're doing in this video is trying to understand what's happening. So let's use what we have. We know that the derivative of x cubed is drop the power, subtract 1 from the power, 3x squared. And now when we integrate 3x squared, we return to the original function. So we integrate 3x squared, we return to x cubed plus some constant c. And that's because, integration is essentially, you could say, the opposite of differentiation. So if we have the derivative, we integrate it, we go back to the original function that we differentiated. Okay, so what is the operation that would take us from the derivative back to the original function? It's integration, but how can we find it without knowing that the original function is actually x cubed? When we found our derivative here, we brought down the power here such that it's multiplied by this x term, and we subtracted 1 from the power. Let's do the inverse of all those operations. And what that means is, let's take our derivative and do the inverse of all those operations. We started by subtracting. To reverse that operation, we add 1, and then by adding 1 we would get the cubed. So we're close to our original function, which is x cubed. What's something else we can do? Well, we can divide by 2 plus 1, which is basically, let me take it here, 3x cubed divided by 2 plus 1 is equal to 3 over 3x cubed, because 2 plus 1 is 3, and we have our original function, x cubed. So that's the process that occurs when we integrate a function raised to some power here, like x squared with the constant here, 3 is a constant. So this is the process. Let's generalize this. So for derivatives, we know, when we want to differentiate some function of this form, drop the power, subtract 1. When we integrate a function in this form, dx, we get x to the n plus 1 over n plus 1. So we're basically doing the inverse of what we did to differentiate, so that we can work backwards. We subtracted when we differentiate, and we multiplied by n when we differentiate. Instead here, we're going to add to the power and divide by that. Let's take an example. The integral of x to the power 4 dx. We know our rule is integrating a function of the form x to the n would have to be this way. Again, we're working backwards, reversing all the operations that have been done during differentiation. So we use this rule. We know our n is 4, so 4 plus 1 divided by 4 plus 1 is equal to x to the 5th power over 5, plus constant c. So it could be anything. It'll just disappear when we differentiate the function to get to this. And x to the power 4, which we're integrating, and we could check our answer. So let's say we differentiate x to the power of 5 over 5. Well, we drop the power, subtract 1 from the power, the 5s would cancel out, we get x to the power of 4, which is what we were integrating, x to the power of 4. Now let's apply that to our integral above. This is equal to x, n is 2, so we add 1, because when we were differentiating, we were subtracting. So now we're doing the inverse of that. We add 1, we have a 3 here, don't forget that, the constant, divided by 2 plus 1, which is equal to 3 over 3, x to the power of 3, plus c, x to the power of 3, plus some constant c. So what we've done here is, remember, differentiating, we did subtraction and multiplication. When we integrate, we're adding and dividing to do the inverse of these operations. Now the second method of integration for this video is the method of substitution, also known as u substitution, because we use the variable u during our substitution processes. So this method is often used for composite functions. Here's how. So let's say we differentiate this composite function f of g of x. We would get by the chain rule f prime of g of x times g prime of x, and then integration again could be thought of as the inverse of differentiation. It's the antiderivative. It brings us back to our original function after it's been differentiated. So we differentiate this derivative that we have, or this function, f prime of g of x times g prime of x dx, we would return to our original function. And you see, and we certainly see here that there are composite functions. U substitution is used when we have composite functions, and when we have a function and its derivative within the integrand. So if you have a look here, the integral of f prime of g of x is a function, times g prime of x is the derivative of g of x. Let's apply u substitution. How are we going to do that? Well, we would let u be equal to g of x, not its derivative, g of x. And here's why. Du is equal to g prime of x dx. That's correct. Differentiating u with respect to x, we know u is g of x, we would get this. Okay. Now, these are called differentials, and I wrote these differentials in this way. It looks like I've multiplied both sides. I'm not going to elaborate on that. It's a separate topic, but it's permissible for what we're about to do and what we want to achieve here. Our integral will then turn into g prime of, instead of g of x, u, because u is equal to g of x. And notice, du, because now our variable is u, so we need to differentiate with respect to du. Are we allowed to do that now? Yes, because if you notice, du is equal to g prime dx, and we have a g prime dx here in our original integral, which du is equal to. So we can substitute du for g prime of x dx. So that's all good. And when we take integrals, we're finding the original function. After it's been differentiated, we're finding the original function from its derivative. So here, that's essentially what's happening in integration. So here, if we have our f prime of u, that means the original function is f of u, because differentiating this would give us f prime, integrating takes us back, plus some constant c. Great. And now, let me move this up here. We know u is g of x, so we just have our original function. So instead of u, we have g of x, and we have f of g of x plus c, which if we differentiate, we would return to our original complicated expression up here by the chain rule. But then when we integrate that, we return to this, and we used our u substitution. You might find it complicated, like when should I use u substitution? But as I said, it's when we find a function and its derivative, g of x, g prime of x. For instance, if we have composite functions, just like what we've seen here. So we're kind of reversing the chain rule. By the chain rule, we get this huge complicated expression, f prime of g of x times g prime of x. But then using u substitution, we were able to arrive at this simple version of the integral, sort of reversing all these chain rule operations until we get to the final answer, the original function. Let me show you an example that would make it easier to understand. So we can use substitution here. Why? Well, the first thing we notice is that we have a composite function, and it's useful to also notice that there's a product here, right? So composite function, something multiplied outside, must be the relationship where we have f prime of g of x times g prime of x. We get to this point with the chain rule. We certainly do have this situation here. Notice, since this is a very complicated expression, I'm going to let u be equal to the inside function here, 2x cubed plus 5. This implies that du is equal to 6x squared, differentiating each term, dx. This is just the power rule of derivatives. We have 6x squared dx in our integrand. 6x squared is here, dx is here, so we can make that substitution. So our integral then becomes the integral of, so we said u is 2x cubed plus 5, so that means you would have u to the power of 6 instead of, so because we substituted u for 2x cubed plus 5, so u to the power of 6 times du. Well, we already know what du is and why we're able to do this. Apply the power rule, plus c, substitute 2x cubed plus 5 for u, 2x cubed plus 5 to the power of 7 over 7 plus c, because we know u is what we have right here. And we found our integral. I want to also strengthen your understanding of u substitution and why it simplifies, why it's sort of a reverse chain rule, why it simplifies the problem for us. Now, we know, again, integration is the opposite of differentiation. And in this case here, we can reasonably say that differentiating this expression would give us this expression, which is why when we take the integral of this expression on the left-hand side, we return to the original function on the right-hand side. So again, if we differentiate by the chain rule, we would get 6x squared times 2x cubed plus 5 to the power of 6. Do it yourself by the chain rule. You'll notice you return to the derivative of the function, which we were integrating to find the sort of original function. So this proves to us that we've returned to the chain rule. Notice, our original function is a composite function, which is why we apply the chain rule. And we get the derivative here. We use u substitution to get back to our original function, because u substitution helps us sort of simplify the expression that we're integrating by creating this sort of reversed version of the chain rule. The third integration method, using trigonometric identities. When we have an integral of a trigonometric function that looks rather complicated, we can use trig identities to simplify it. Show you a quick example. Okay, the integral of sine squared x. How can we find it? This can be expressed as sine x squared dx. So can we use u substitution? Well, we can't really apply u substitution here because we don't have this situation exactly, where we have a function and its derivative. Function on the inside, derivative on the outside. So what we would have to use here is trig identities to simplify the problem. Rewriting stuff. Sine squared x, how can we rewrite that? Well, we know that cosine of 2x is equal to 1 minus 2 sine squared x, if you know your trig identities. And then we could solve for sine squared x. So sine squared x can be written as 1 minus cosine 2x over 2, which is equal to 1 over 2 minus cosine of 2x over 2. So let's use this, plug it in up here, because they're equal, and let's integrate. So we can rewrite this as the integral of 1 over 2 dx We're kind of splitting up our integral into two. So we'd have cosine of 2x over 2 dx. Here, application of the power rule, 1 over 2x, because if we differentiate 1 over 2 times x, we would get to 1 over 2. So our original function is 1 over 2 times x. We can take out the constant here, which is a half. Cosine of 2x dx. Okay, now we can also apply u substitution, because we have 2x, which is a function, inside another function, and we have its derivative out here. Obviously we have a 2 multiplied by x, but the constants can always be ignored, and then we can multiply the constant by the expression at the very end of our operation, whether it's integration or differentiation. So we can ignore the constant, and we have 1 here. 1 is the derivative of the function x, so we can use u substitution. U is equal to 2x, implies that du is equal to 2dx, which means dx is equal to du over 2, dividing both sides by 2 here. So we get 1 half x minus 1 over 2 cosine of u, because 2x is u, du over 2. You can take this constant out again, so we would have 1 over 2, which is just multiplying these two, we would get 1 over 4. Then we would get 1 over 2x minus 1 over 4. Integral of cosine u is sine u, because the derivative of sine u is cosine u. And we have our plus c. Simplify 1 over 4 sine of u is 2x, so we have a 2x here, plus c, which is a constant. Great, we found the integral using power rule, u substitution, and rewriting the expression that we had in the very beginning.